Section 46 is triple integrals in cylindrical and spherical coordinates. First problem we'll do, it will be in cylindrical coordinates, and it's just a standard triple integral. The big difference is there's no x, y's, and z's, but rather r, thetas, and z's. So like always, we do the innermost integral first. That is, we do that integral. It's in terms of r, so cosine theta is just a constant. If you like, you can bring it in front of the integral sign, cosine theta. So this is no longer here. Well, when we integrate r dr, we get r squared over 2. In this case, from 0 to 2. d theta dz. And when you plug in 2, you get 2 squared over 2, 4 over 2, which is 2. When you plug in 0, you get 0. So it's 2. Now 2 being, so this here is just 2. Now 2 being a constant, it's not a function of theta nor z, can go way in front. You have 2 times the double integral of cosine theta d theta dz. 0 to pi over 2, 0 to 4. And we do the innermost integral first. We're integrating with respect to theta, and that is a function of theta, which is good. The integral of cosine theta d theta is sine theta from 0 to pi over 2. If you consider your sine function, pi over 2 is right here, so sine of pi over 2 is 1, and the sine of 0 is 0. So it's just 1. It's just 1. So we have 2 times integral from 0 to 4 of 1 dz, or just dz. The integral of dz is z, from 0 to 4. You plug in 4, you get 8. 2 times 4 is 8. Minus 2 times 0 is 0. 8 minus 0. This happens to be the number 8. Let us do an integral in spherical coordinates. Again, it's just different letters. There's a lot of meaning behind it, but for just evaluation, it doesn't matter. The integral from 0 to 2 pi of the integral 0 to pi over 4, integral 0 to cosine of phi, rho squared sine phi d rho d theta d phi. Okay, we do the innermost integral first with respect to rho. You have rho squared times sine phi. Since it's a product and sine phi has nothing to do with rho, we could factor it out. Sine phi. If you think about it, possibly you could have brought it in front of that second integral. So right now it's integral. You may or may not be able to. I'm not even deciding that. Sine phi excuse me, 0 to pi over 4 sine phi. Now, the integral of rho squared d rho is rho cubed over 3 from 0 to cosine phi d theta d phi. Here you're going to get cosine cubed phi over 3 minus 0 cubed over 3, which is 0. So this is what we get. The 1/3, I'm going to factor out in front. If you call cosine of phi u, if u is cosine of phi, then du is not sine. Okay, what's in here is not a function of theta. And I was premature talking about what I was just talking about. What's in there is not a function of theta. That is, it's a constant. The integral of a constant times d theta is that constant times theta. And theta goes from 0 to pi over 4. When you plug in pi over 4, you get the constant times pi over 4 minus the constant times 0. That's just the constant times pi over 4. The pi over 4 I can bring all the way in front, and that becomes pi over 12. 1/3 times pi over 4 is pi over 12. Times the last integral from 0 to 2 pi of sine phi cosine cubed phi d phi. I just felt like writing cosine cubed phi first. Sine phi d phi. Well, again, if I call u cosine phi, well then du is not sine phi d phi, but rather negative that. So this here will be u cubed. But sine phi d phi, it's not exactly du. If I multiply by a -1, inside and outside, now it is correct. So let me go to the top line, please. Let me erase the top line, and then I'll go get a right. So we have u cubed times du with a negative cosine pi, a negative pi over 12 in front. We have a negative pi over 12 in front. It's u cubed du. That integral is pretty straightforward. It's just u to the 4 over 4. And u happen to be cosine phi from 0 to 2 pi. Now, I hate having that negative in front. It's just the way I am. And I'm sure for most of you it's going to be very, very awkward having that negative in front and dealing with it. So what I do is I multiply this by -1, and I get just pi times cosine phi to the 4th over 3 over 4, 12 times 4, or 48. That is, I just ignore that negative sign. But then you have to switch the limit of integrations. Instead of from 0 to 2 pi, you just switch it 2 pi to 0. Thing is that cosine 0 is 1 and cosine 2 pi is 1. That is, in either case, we get pi over 48 minus pi over 48, which happens to equal the number 0. So there is an integral using cylindrical coordinate values and spherical values. Now, in this problem, we're going to look at a rectangular coordinate system. When we be given an integral in rectangular coordinates, and we want to write it in spherical and cylindrical coordinates. Now, what the integrand, what you're taking the integrals of, really has nothing to do in this. Nothing at all. Now, z, so the innermost integral is with respect to z. So z goes in between 4 and x squared plus y squared. Now, first we're going to go to cylindrical. Now, in cylindrical, x squared plus y squared is r squared, and 4 is 4. In cylindrical, you get to have z's and r's and thetas. Z's, r's, and thetas. Okay, so this innermost integral is just integral from r to 2. X becomes r cosine theta. So we get r cosine theta dz. Now, dy dx, that always comes dy dx or dx dy, they both become r dr d theta. They both become that, r dr d theta. Maybe I shouldn't say dy dx equals dx dy, but they do both equal r dr d theta. Okay. Now, the next part, the next integral, it says that y goes between here. Well, y goes between negative 4, the square root of 4 minus x squared, and positive the square root of 4 minus x squared. If I square everything, I get that y is positive, but it's less than, that's not true. Just don't know how to say it, but since y can be both negative and positive, you get that x squared plus y squared is 4, and that x and that y can be both negative and positive. And x goes between negative 2 and positive 2. I mean, we know that those two pieces give us a circle. And since x can go from negative 2 to positive 2, it can either be the top half or the bottom half, or both. And since y can both be negative and positive, y can be positive, it can be negative, it's the whole circle. So r goes from 0 to 4 because the radius of the circle is the square root of 4, which is 2. So, excuse me, r goes from 0 to 2. And then the theta it goes all the way around. It's the whole complete circle. So it goes from 0 to 2 pi. If this here would have been 0, that is, y goes from 0 to the square root of 4 minus x squared, then if this were 0, I would still get x squared plus y squared equals 4, but y has to be positive. That is, I would only get the top half of the circle. And then theta would only go from 0 to pi. Everything needs to fit together like a glove. Okay, so that's this integral right here. That's how you convert the top integral to cylindrical coordinates. Now we want to go to spherical. Spherical is when we use rho, phi, and theta. Now, in spherical coordinates, it turns out that dz, dy, dx, or any order is equal to rho squared times the sine of phi times d rho, d phi, d theta. And it also turns out that x is equal to rho sine phi cosine theta. But that's exactly this here. So I guess this does come into play. I was mistaken when I said it doesn't. So I have to multiply those 4 items. That is, I need to multiply this with that. Well, rho times rho squared, that's rho cubed. Sine phi times sine phi, that of course is sine squared phi, times cosine theta, d rho, d phi, d theta. Okay, so we have that. So what does rho go between? Rho. Now, we know that the cosine of the angle, the cosine of phi, we know that the cosine of theta is always z over rho. Solving this equation for rho, rho is equal to z over cosine theta. Bringing the cosine theta to the top, remember cosine theta in the denominator is secant theta in the top. So that is rho. Rho goes from one z secant theta to another z secant theta. Now the question is, what does z go from? What does z go from? Now, if you look at the original integral, z, it goes from x squared plus y squared to 4. The least z can be is 0. So, rho is in between 0 secant of theta, which of course is 0. Multiplied by 0, you get 0. And the upper value for z is 4. So, plug in 4. 4 secant feet. So rho goes from 0 to 4 secant feet. You must know this here, or at least know this and solve for rho. Rho goes from 1z times secant of theta to, from the lower z times secant of theta to the upper z secant theta. Okay. So now we have the rho limits. What about phi? Now phi goes from 0 to pi over 2. And remember, phi is the angle that you make off of the z-axis. Now, we know that z, looking at the very first limits, it goes from x squared plus y squared to 4. That is, z is equal to x squared plus y squared, or z is bigger than x squared plus y squared, up to 4. Well, when, consider z equal x squared plus y squared. If z is 0, then you have a circle of radius 0. If z is 0, then x squared plus y squared is 0, and you have a radius of 0. If z is 1, then at a height of 1, you have a circle of radius 1. When z is 4, x squared plus y squared equals 4, you have a circle of radius 2. Basically, you get something like this. Okay, let us draw this as big as we can, and then we can talk about this particular angle. Let this be the z-axis. Okay, for this point here, that is the angle. This is angle phi. This is the angle phi. Okay. Now, first phi can be 0 degrees, and then bigger, and then bigger. This gets bigger and bigger. Now, as you get to this point here, the angle is going to 90 degrees. 0 to pi over 2. First, the angle here is 0 radians, and then it's a little bit bigger, and then it's bigger, and then it's bigger, and then it's bigger and bigger. Goes between 0 and pi over 2. If you want to say, well, what about the left-hand side? Not a problem. Here's the z-axis. This angle is pretty small. This angle's a little bigger. This angle's even bigger. This angle's bigger, biggest, and it goes up to 90 degrees. Okay. Now, what does theta go between? Theta is in the xy plane. Theta is in the xy plane. Now, with respect to the xy plane, all you have are circles. All you have in the xy plane are circles. Remember, this is the z-axis. That's the z-axis. Now, the xy plane is right below it. Perpendicular. The z-axis is perpendicular. If you reflect this onto the xy axis, you just get a circle. If you project this onto the xy axis, you get a circle. This, a circle. And for each of those circles, it goes all the way around. The angle theta goes from 0 to 2 pi. And there is an example of converting that top integral to cylindrical coordinates. One more. Suppose you have a triple integral like this. Okay, x dz dy dx. Let us go to our cylindrical. So it too will be a triple integral. Cylindrical has z's in it, so z's won't change. And it has not p, excuse me. It has theta and it has r's. So since we're integrating first with respect to z, things won't change that much. In fact, we'll even have our dz. And z goes from a to the top limit. A plus the square root of a squared minus. Now, no more x's and y's. You can have z's, but no more x's and y's. But x squared plus y squared is r squared. Okay. And let me just move out the dz to the right a little bit. Now, x is r cosine theta. X is r cosine theta. And dy dx, that becomes r dr d theta. Okay, so dz is the first integral. That means these limits are z's. And now we have r. Well, and then we have theta. So what does r and theta go between? Well, y goes between these two. Need to start catching on. That's a circle of radius a. Maybe it's the top half, maybe it's the bottom half, maybe it's the left or the right. It's some combination of these four pieces. This piece, this piece, this piece, that piece. It might be all of them. It might just be this piece and that piece. Though I'm not sure how that one can happen. But it's some combination of those four pieces. Now, since y goes from negative to positive, we didn't rule out the bottom half or the top half. And since x goes between negative a and positive a, we're not ruling out the left half or the right half. If x just went from 0 to a, it'd be the right half. If it went from negative a to 0, it would be the left half. But it's going from negative a to a. It's the whole entire circle. And the radius goes from 0 to a. What I mean by that is, to get to any point on the circle, you start here where r is 0, and you go out to here where r is a. So r, it goes from 0 to a. And where does theta go to? Since it's the whole entire circle, it goes from 0 to 2 pi. And there it is. You might want to say that that's r squared. R squared cosine theta. So that is how you would go from rectangular, the top integral, to cylindrical, the one that has r's, thetas, and z. I don't say polar, because polar just has r's and thetas, doesn't have z's. Okay. The next integral that we want to convert this top one to is to our spherical coordinates that has rhos, it has thetas, and it has speeds. Now, the theta is good. We know it's not changing. It's between 0 and 2 pi. So that's a little bit helpful because we want theta last, so I know the last limit, what happens, the outermost limit, it goes from 0 to 2 pi. Now, we just did this one in the last video, x, dz, dy, dx. We just did that one. That's rho cubed sine squared phi cosine theta. If you figure out how we got that, just back up the video. Okay. Now, what does rho go from? What does rho go from? Now, we know that rho is in between z secant phi and z secant phi. Is what does z go from? What does z go from? So the question is, let's draw z. We know from the top, z goes from A to there. We know that z goes from one thing to another. Okay. Z. Now that's y and that's x. Now z starts at A. Okay? A. Now, what happens after A? Well, it goes to A plus this. A squared minus x squared plus y squared. Let's just forget the A for a moment. Okay, so that's what z equals. Let her solve this. So z minus A is equal to this square root stuff. If I square it, z minus A equals A squared minus x squared plus y squared. If I bring the x squared plus y squared to the other side, we get x squared plus y squared plus z minus A squared is equal to A squared. The center, what makes this 0? 0. What makes this 0? 0. What makes this 0? A. That's the center. That's the center. And we have that z is positive, because z goes from A to above. So what you get is the upper sphere. You just get the top half of the sphere. What's above A? You get the top half of the sphere centered at 0, 0, 8. So let us draw this yet again. Here's A. You get a sphere. Okay. Now, the question is, what can phi go from? Now remember, out here is A. This distance is A. This distance is A. This distance is A, and this distance is A. May not look like that in the picture, I'm sorry, but nonetheless it's A. So, first, theta goes, or phi goes from 0, and then it gets bigger, got bigger, and bigger, and bigger, and the biggest. Now, what is this biggest? Well, remember, this is A, and this up and down here is A. I want to draw this, again, I want it to be crystal clear what's going on. This is A, and that's A. And there is our hemisphere. This angle that I just drew, this angle is 45 degrees, because this is A and this is A. It's a 45-degree triangle. Theta goes, rho goes from 0 to pi over 4. So somehow we got into rho. Sorry about that. Rho goes from 0 to pi over 4. And I said that rho is in between the smallest z value times secant phi times the largest z value, secant phi. The lowest value that z can be is along here. That's where z is A. Okay, so this is A, secant phi is less than or equal to rho. Now, what's the upper value for z? Well, the largest point I see here on this graph is right here. It's right there. Now remember, this here is a radius. It too is A. Well, if this piece is A and this piece is A, then the biggest that z can be is 2A. So z sub 2 is 2A. Secant phi. It goes from A secant phi to 2A secant phi. There is a second example, converting an integral in rectangular coordinates to polar and, to cylindrical and spherical coordinates. And that finishes this section.